Welcome to the campus of North Idaho College and today's broadcast of the North Idaho College Public Forum. The crew is comprised of North Idaho College television students. Your moderator is North Idaho College political scientist, Tony Stewart.
Today we complete a 3-week series with the Department of Geology from Eastern Washington University. As you know, during the past 2 weeks we've been discussing many aspects of geological characteristics of our area, and today we wish to discuss the exploration, identification, value, and use of Pacific Northwest minerals. In order to accomplish this task, we welcome to our program 2 members of the faculty from that department. First of all is Professor Martin Mumma, and secondly is Professor Mohammed Ikramuddin. Gentlemen, welcome to our program. Joining with me in questioning our guests on this important subject is, first of all, member of the faculty at North Idaho College, Richard Snyder, and regular panelist, Janelle Berg. We'll proceed to questions at once, and I shall invite Janelle Berg to commence the questioning.
Professor Mumma, most of us do recognize the value of gold and silver, but very few of us know about uranium or exactly what the value might be. Can you tell us what the value is, why it is that it's such a sought-after mineral?
Yes, primarily uranium is used as a fuel source, of course, for radioactive elements that are used in reactors to generate electricity. Other than that, there is a small amount that is used in medicine, irradiation, chemotherapy, but by far the largest value of it is for generation of energy. Go ahead.
Where do you find uranium in this particular part of the country, in the Pacific Northwest?
In the Northwest, unlike many of the areas where uranium has been plentiful in the past, for instance, the Colorado Plateau, Wyoming, Utah, and those areas, uranium here is located reasonably close to igneous source bodies, hard rocks that have been crystallized at considerable depth and have now reached the surface and carry with them trace amounts of uranium. The uranium in these trace amounts is not economic because the concentration is simply too low, but because of its exposure at or near the surface, groundwater percolating down through these particular kinds of rocks leach the uranium minerals out, transport them to other locations, and then they're concentrated in more favorable host rocks. So a geologist who is interested in looking for and exploring for uranium tends to look for the source rocks, knowing that they will not be of economic value, but also realizing that in proximity to these source rocks there is an excellent possibility of obtaining economic deposits of that particular commodity.
Where in this particular area of the Pacific Northwest would one be likely to find deposits of uranium?
We have 2 active uranium mines in the Pacific Northwest now. There is another one that has been located that is not in production. The 2 active ones are the Midnight Mine, which is formerly called the Dawn Mine, and it's north of the Spokane River on the Spokane Indian Reservation. The other one is a Sherwood mine just immediately off the Spokane River. Both are presently producing uranium.
I believe that you have some slides with you that will show something about the uranium, and would you care to show those at this point?
Sure, that might be the best way to get into the whole topic. We'll begin to look at a series of slides that will illustrate where uranium is presently being produced, a little bit about the genesis of it, and some of the exploration techniques. The slide that you see before you now is a rather messy, complex geological map, and the value of this is probably to point out the location of the Midnight Mine in the lower right-hand corner of the map, and immediately below that, which is practically invisible, is the position of the Sherwood Mine. Now the next slide shows a little bit closer view of the geology involved around the Midnight, and we see a variety of rocks exposed here. The source rocks from the Midnight Mine are granitic rocks that are technically called either quartz diorites, granodiorites, quartz monzonites, and are rich in silica, rich in potassium, and have in them trace amounts of uranium minerals. The uranium minerals are leached from these rocks that are called, in this particular case, noted KP on this diagram, and then transported to more favorable host rocks. Now the next slide is an aerial view of the present workings of the Midnight Mine, and we're looking north-northwest. It's an open pit operation, fairly extensive, and they are moving several thousand tons of ore-grade material a day. They have a concentrator and a refinery reasonably close, within about 6 or 8 miles of this particular site. So the ore is mined, carried by trucks to the refinery, and they're reduced to a product that's called yellow cake, and it is then barreled and shipped to the consumer for further refining. The next slide is a picture of the prime mineral there, which is pitchblende. It's U308. It's a rather dense black sooty material, and I have here on the desk in front of me a hand specimen of that might show better than the slide. It tends to be very sooty and crystalline in nature and extremely radioactive. It's easily picked up with a Geiger counter. Next to that is a more beautiful kind of uranium mineral called autunite, and in addition to being beautiful, it's extremely soluble. So in some areas where this is exposed at the surface, particularly in the winter, and as the spring thaws begin and the snow melts, why, the snow will become stained green, very light pale green with this particular mineral. The next slide in this sequence is another slide of pitchblende. Shows the vein character of it, and normally the concentrations of the uranium ore minerals in these ores is very, very low, yes, less than 0.5%. In some cases, the grade will go up to 2 to 3 to 4%, which is exceptionally large. The next slide is a diagram showing the relationship between the source rock on the left of this diagram, which is granitic, it's a quartz monzonite, called granite here, and the host rock, which is the ultimate location for the ore that is produced. The way the minerals get from the left to the right is by a process of groundwater percolation, where uranium minerals are picked up in acid solutions. Since most uranium minerals are very soluble, they're carried away from the source, concentrated in an appropriate host, usually where those particular acid solutions go into a basic environment and are simply precipitated out. They assume very strange forms and shapes, as these slides indicate. The next slide is a diagram showing concentration of ore minerals and the position of the ore relative to the bedrock. And the colors indicate grade in this, with the blue being high-grade material. And you can see that the ore body conforms to a basement sort, or a floor, below which it does not percolate. And it's thought that groundwater carrying these minerals through here simply concentrate them and build up a very favorable area to do it. The next slide is a rather artsy-craftsy depiction of what this ore body might look like if everything else were stripped away. And it's kind of a gossamer-looking thing. And that is a reasonably good illustration of what the whole ore body might look like. The next one is another shot of the mine, the pit. On the left-hand side is the source rock that's light-colored, the granitics. On the right-hand side is old, metamorphosed, very carbonaceous-rich rocks that act as the host and the concentrator to the minerals as the groundwater percolates through. The next slide is another diagram of an ore body showing again the relationship to the granitic source on the left and the shape and character of the ore body on the right. And the next one is a very simplified model of how this situation and this whole system might work. Groundwater coming through the porphyritic quartz monzonite there on the left picks up trace elements of uranium, carries it into the depositional position, in this case a togophyllite it's called, and there it encounters a different sort of a physiochemical environment in which the acid conditions are not stable. They go into a basic chemical environment, and the uranium minerals are precipitated out and in concentration. The next slide is a shot of the Sherwood mine, just visible in the center right of the picture, and the Midnight mine in the upper left. And it's thought that the Sherwood mine is actually producing uranium that was derived from the Midnight mine. There is an old river channel system that connected these two, and percolating groundwater came simply from that area down into the Sherwood position and deposited minerals again. The next slide is a shot of the Sherwood showing their open pit operation. It's a smaller operation than the Midnight, but is a very active producer right now. The next one is a close-up of some of the minerals and the ore deposits at the Sherwood. The next one gets into a discussion of the genesis of these minerals. We'll try to keep this reasonably low level so we can understand a little bit of what's going on. It's thought that a lot of the source material that have uranium minerals in them were originally produced, as Dr. Keever was talking earlier in the previous program, in old areas where one plate is being pushed beneath or subducted beneath another lithospheric or continental plate. And that as the material, the next slide please, as the material goes beneath one plate, and for instance we'll use this illustration B in the lower left-hand corner, the dark line on the left illustrates an old trench system, much like the one that exists off the coast of Southern California, the Andes, and from Vancouver Island on north, where one lithospheric plate is being shoved beneath another one, and the point of injection is from your left to the right, creates a submarine trench. That material goes down to at least 700 kilometers, and when it reaches about 120 kilometers beneath the area on the right, or the continental United States, it begins to melt, and the material in that melted plate comes to the surface and forms, as we know now, the Cascades, is responsible for a lot of the volcanic activity that we see, but is also responsible for the emplacement of the kinds of rocks that we just saw before, which carry these trace element of uranium. The next slide shows what the North American continent may have looked like back during the time that we think the source rocks were in place that carry the mineralization at the Midnight. Now this was back about 45 to 50, 60 million years ago. We can see that the continental margin was further to the east than it is today, that the Cascades really had not formed to any appreciable extent, and that because the lithospheric plate, which was then called, an old plate called the Farallon plate, was shoved beneath the North American continent, we began to produce volcanism. In fact, in the Eocene, or this 40 million years ago, there was extensive volcanism all over the Pacific Northwest, and produced also a tremendous field of volcanics in Idaho and Utah called the Chalice volcanics, and probably in place the granitic body that we see now that produces the minerals. The next slide is just going on a little bit. No, it's going back in time a little bit. This is in reverse, but that's all right, to show again the old topography and the paleogeography that existed back when a lot of the activity was taking place that produced these uranium minerals. The next one quickly just shows a cutaway view or a cross-sectional diagram of what that plate may have looked like as it's being shoved beneath the North American continent. This was 60 to 50 million years ago. 50 million year event is the one we think, again, is responsible for the emplacement of the Midnight source quartz monzonite. The next one is a little bit earlier in time, showing that the plate regime changes, and these plates are constantly migrating back and forth. And this 90 million year event, or late Cretaceous in age, emplaced another granitic body a little bit to the south of the Midnight mine, which originally was thought to have been the source, but now we think that it is not. The next one. And now we come to some of Mohammed's slides, I think, and my slides end right there.
I would like to inform our viewers who might have joined our program in progress that we're talking to faculty members from the Department of Geology at Eastern Washington University, and today's subject is exploration, identification, value, and use of Pacific Northwest minerals. We shall invite Richard Snyder to continue the questioning.
Professor Ikramudin, what is hydrogeochemistry, and how do you use it to explore for gold and silver deposits?
Recently, there is a great demand for gold and silver, and as you know, the prices are shooting up. Therefore, the interest in gold and silver has increased tremendously. Therefore, various companies, they are trying to develop some exploration method to locate more silver and gold deposit. Therefore, most of the techniques they are used presently, they use either soil or stream sediments or the rocks, analyze them for gold or several other elements. Now, water also can be used as a very useful technique to locate various types of deposits, but the concentration of various elements in water is very, very low. Therefore, it is difficult to analyze for the elements in the water and needs specialized types of technique and specialized types of laboratories. And particularly in the case of gold and silver are very, very low concentration compared with the most of the other elements. Like rocks and soils, it is at parts per billion level. In the water, it occurs as parts per trillion level. Therefore, very few countries have tried to use water as a technique to locate gold and silver deposit. And Russians have developed several techniques and successfully located gold-silver deposits with the help of hydrogeochemical techniques. But the United States or Canada or Western European countries, there are very, very few studies carried out and they have not been very successful. Therefore, with the intent of this, we thought it may be worthwhile to develop some techniques which can be used to locate gold and silver deposit. Therefore, to do that, we collected stream water sample from a known mineralized area from Republic Graben in northeast Washington. And about 52 samples we analyzed for gold, silver, and arsenic as well as silicon with the help of atomic absorption technique. Therefore, gold and silver in these waters is very, very low, ranging from 1 parts per trillion to 100 parts per trillion or more. Therefore, most of the techniques which are used are neutron activation techniques to analyze at that low level water sample for gold and silver. And these type of techniques, they are not much available and they are very expensive and you need a use of nuclear reactor. Therefore, such type of facilities the companies cannot afford to use and it is very expensive. Therefore, we spend a lot of time to develop some of the technique which will be simple, rapid, and can be utilized by more people. Therefore, after trying several months, we were successfully able to develop some methods with the help of what is called an electrothermal atomic absorption, or which is also referred as graphite furnace. Therefore, we analyze all those 50 samples from the known mineralized area, and we selected about 17 samples from the areas where gold and silver is mined. And all those samples, they show abnormally high values compared with the water samples collected from the non-mineralized area. Therefore, this study has successfully demonstrated that the chemical analysis of gold, silver, and arsenic in water sample can successfully be used to locate gold and silver deposit. Therefore, this technique we have also presented recently in Vancouver in symposium, and several people, they are really very interested to do some work in those lines.
Did you bring some slides with you?
Yeah. Therefore, this slide shows the location of the gold, silver mines in the Republic area in the Washington. Next slide shows the various values in gold, silver, arsenic, as well as silica, and you can see they are very, very low. In the case of gold, is 0.01 ppb to 0.14 ppb. That means 1 parts per trillion to 140 parts per trillion. Next slide, please. In this diagram, you show the correlation between gold and silica. Therefore, this is the new technique we use to find out the anomalous samples. So all those samples which are the filled circle, they are the background sample having very low values of gold, but all the samples which are shown in triangle, they show very high values. Therefore, by plotting gold against silica, we will be able to find out collect those anomalous sample. Otherwise, it is not possible by using the normal technique. The idea is when the rocks are weathered, silica and gold are also released from the minerals in the rocks and they are dissolved in the water. Therefore, whenever silica in most of the rocks is about 60 to 70%. Therefore, the highest silica can be 100%, but the gold in that type of rocks is about 1 parts per billion. But whenever gold concentration is more, it can be 100 or 1,000 times more. That way, the anomalous sample will release more gold, and you will see that type of pattern in that. In the next slide, we show similar thing again, silica and silver, and here also you can see all the samples which are background. They show good correlation, but the anomalous samples showing triangle, they fall quite above the line. The next slide, this shows the plot of arsenic and silica. Therefore, arsenic is an element which is mostly associated with gold. Therefore, we thought that element also may be helpful to look at gold deposit. This also shows similar pattern like gold. Next slide. In this slide showed all the location of the samples where we collected water from the streams. Next slide. These are the maps showing the anomalous areas where gold values were found very high. The next slide. This is another slide showing the arsenic values we found higher than the normal. Next slide, please. This is the slide showing all the three types of anomalies in the areas. All those circled or outlined areas, those are the areas where most of the mines are located. Therefore, all the water samples collected under those areas, they show very, very high concentration of gold, silver, as well as arsenic. Next slide, please. Oh, this is another program related to uranium.
Okay, fine. Would you like to continue the question, Engineer Berg?
Yes, we often have wondered, is there a shortage of uranium? Is there a shortage of precious metals? We hear a great deal of talk about this. Perhaps I'll start with Professor Mumo.
In the United States, there isn't a shortage of uranium. We have uranium reserves presently held by many of the major oil companies and some of the larger industry, nuclear energy industries that can far exceed our present demands. We have such government control at this point that it is simply not economically feasible to do a tremendous amount of uranium exploration. In the last 4 years, uranium exploration has dwindled considerably, although there are several of the major companies still doing quite a bit.
Where else in the world is uranium found?
Where is it found?
Pretty much everywhere.
Yes, in a great many areas. Practically all of the countries, the continents that we know, have sizable deposits of uranium. Australia, Russia, Africa have sizable deposits.
Is it necessary, is the same situation true with gold and silver, and is it necessary to have both for certain kinds of production, such as certain kinds of energy production? Is it necessary to have both the gold and the silver and uranium as well?
Yeah.
And how does this work? How do you put them together? I guess is the question.
Well, uranium is usually used for energy, but gold and silver not for energy, but used for mostly industry as well as for other purposes, and has a monetary value rather than used for energy purposes.
Okay, I think of uranium and I think of various kinds of energy, and I also think of radioactivity. Can you put my mind at ease? Or is it true that uranium is?
Yes, it is radioactive. This particular piece here in front of me is radioactive. It is emitting considerable quantity of radioactivity right now, but not at a level that I could sit here and hold it for a long, long time and it would not bother me. In fact, my skin would trap most of the radiation coming from this, and the amount that penetrates is hopefully not that much. So, no, it is radioactive. In the natural state, it is not harmful. It's only harmful when it becomes concentrated at very high levels, and then only when it reaches a thing that's called critical mass state. where it can become explosive, which
So
is...
in mining, it wouldn't be dangerous for those mining it.
Yes, it is dangerous to the point that as any foreign subject, you would not want to breathe it into your system, so that all the miners then are protected. They do wear protective clothing. There are stringent restrictions about what you can and can't do in uranium mines. So I think most mining people, particularly today, are very aware of the dangers involved and take adequate precautions to prevent any injury to themselves.
I have another question along those lines, and then Richard Snyder will conclude for us. I was wondering, concerning, since we're such a mineral-rich area in silver and gold and so forth in North Idaho in particular, I'm thinking of, with your expertise in the area, how long will we have this? I hear political reports from Washington, D.C. that we'll have mineral shortages in the future, and it will be part of our economic crisis as petroleum has been. What does it hold for us in the future in this area in the minerals?
Yes, there are mineral shortages now, and we will have mineral shortages in the future. Gold and silver at the present time is not short in the sense that it is really useful to anything other than an intrinsic sort of a value and a base for our money. It is used, of course, in the photographic industry, for jewelry and things, all of which we could really do without if we had to. The other minerals, though, that are in short supply, in critical short supply, are going to impose an increasing burden on our economy in the future simply because of practices, governmental practices, for the most part, that have been followed in the past.
You mean if we change government policies that we would not have the problem? Are you saying
that would be a big step toward solving some of the problems?
The
yes.
deposits are still there?
Yes, they are.
Richard Snyder.
Why not carry on with policy changes? We now have Ronald Reagan as president and Secretary Watt in the Interior Department. Do you see some of these changes you seem to get a little enthusiasm about? Do you think things are going to change?
I think most economic geologists and industrialists at the time of Watt's confirmation breathed a huge sigh of relief, and probably environmentalists gasped with concern. And some of the policies that are being followed now have probably borne that out. The pendulum has definitely swung back the other way now. It's too early to tell if it has gone too far toward exploration and exploitation. My guess is that it has not, and we're simply regaining some balance. But I think that with the present administration, the climate, the atmosphere for exploration and production, both for hydrocarbons, oil and gas, and for metals, both metallic and non-metallic reserves, are going to be far more favorable. In fact, the Canadians are coming into the United States in hordes now because of the adverse climate for hydrocarbon exploration and production in Canada, particularly Western Canada, and the very favorable climate that we enjoy now in the United States. And the oil business is booming as it has never been before.
I must close on that note. Thank you, gentlemen, very much. I enjoyed the program very much in the 3-week series. The Department of Geology and all your faculty and President Frederickson of your university have been most cooperative, and we appreciate that. Ladies and gentlemen, we conclude a 3-week series with the Department of Geology from Eastern Washington University, and this is a very special program for us in that it concludes our 9th year of broadcast, the academic year. Starting next week, we shall be involved with some reruns for the summer until the fall productions. I hope you've enjoyed the years that we've had in the past and that you'll continue to enjoy this program. I would like to thank Bill Stanley and his crew from North Central High School, Lewis and Clark High School, and Rogers High School, and KSP for allowing us to tape in this studio. Have a good week. I am Tony Stewart.
Your moderator is North Idaho College political scientist Tony Stewart.